So hello everyone, we are studying thermodynamics and we started the topic of mixtures. Our main motive for this topic was to study free energy of mixing. Now, mixtures, as I have told before in the previous videos, are of two types. Broadly, there are two types. First is chemical mixtures and second is physical mixtures. Physical mixtures are the type of mixtures in which the particle this A and B will be there and just it will stay there as it is. It will not react or it will not interact. So these type of mixtures are known as physical mixtures, mix where they will not interact. And there is another type of mixture, that is chemical mixtures. Here, as the name suggests, it will interact. A and B will interact. Now, due to this interaction, there will be some excess free energy associated. So this part alone will be the free energy of physical mix, but due to interaction there will be some excess free energy, and that excess free energy is nothing but this delta G mix. It can also be written as delta H mix minus T delta S mix. Now, before diving deep into chemical mixtures, I should divide things. So chemical mixtures again are broadly classified into three type of mixtures. One is ideal, second is non-ideal, and third is regular. And we'll study them one by one. So let's study the easiest one, that is ideal mix. As the name suggests, it is the ideal mixing of two particles A and B. So ideal mixing means there is interaction, but due to the interaction, there is no evolution of heat as such. We'll talk about in detail about this interaction in the further lecture videos, maybe in the next video itself. But for now, just consider that there is interaction, but there is no evolution of heat due to interaction or absorption of heat. That means this delta H mixing is zero. So this delta G mix will then become delta H mix is 0, so it will become minus T delta S mix. Now, we studied in the previous video that delta S mixing, or I should write in this case, since it is a mixture, there will be some configuration. I can write this delta S mix as delta S configuration, and that was K ln omega. We studied that in the previous video, and this omega is total number of arrangements possible for A and B atoms. So we studied that in the previous lecture video, that this is the total number of arrangement of A and B atoms. Now, if let's say A is Na in number and B is Nb in number, so how we can write this omega? So it can be easily written as omega equals Na plus Nb, that is total number of arrangement possible, and deducting the overcounted ones, that is, since A atoms are identical and B are identical, this will be Na and Nb factorial. So we studied that in the previous video. If you are confused, just rewatch it. Now, this is our omega, but writing things in this way is really clumsy. We need to simplify this. So let's simplify this configurational entropy thing. Now, let us simplify this configurational entropy term. So configurational entropy is K ln Na plus Nb factorial upon Na factorial Nb factorial. So for simplifying this, there will be an approximation which will be used, and that approximation is Stirling's approximation. Stirling's approximation. And what is that approximation? The approximation is ln of n factorial is nothing but n times ln n minus n. So using this approximation, this term will become something like this: ln Na plus Nb minus Na minus Nb. plus, sorry, there will be minus because these are in denominator, so I am just taking minus common. It will become Na ln Na minus Na plus Nb ln Nb minus Nb. Removing the brackets, these will get cancelled out, so I've just cut them out. So before proceeding further, I want to comment one thing, that till now which we have studied, things that we have studied, G, H, entropy, all of them were actually per mole. Whenever you'll solve some example or read books, you'll see them written as Gibbs energy per mole, Gibbs enthalpy per mole, entropy per mole. So all of them were per mole. I have not specifically told that, not to confuse you guys. That's the main reason I didn't told. But the thing is, these are per mole. So if our A and B system, we have to write entropy per mole, I'll consider this system to be 1 mole. This whole system is 1 mole. That means Na plus Nb is nothing but our Avogadro number. So just keep this in mind. This will be used while solving this. So this is our Avogadro number. I'll replace that with Avogadro number. Not now. Let's proceed further. We'll see how it is solved. Now, since this is our Avogadro number, we know that we want to deduce this term. How we can do it? Na plus Nb ln Na plus Nb. We have to reduce this term. We can make this, if we can make inside ln 1, this term will be gone. So for that, I'll just minus Na plus Nb ln Na plus Nb, and since I have deducted another term which was not there, I have to add it to balance things up. Ln Na plus Nb. Now if we see this, if we take plus remaining terms which are here, I will not write them out. Now Na plus Nb is common, Nb is common, we got ln Na plus Nb divided by ln Na plus Nb, it will be 1. Now let's take Na part and combine with this Na, and Nb part combine with this Nb. So we'll get Na ln Na, this is minus, keep that in mind, minus, divided by Na plus Nb, similarly plus Nb ln Nb divided by Na plus Nb. Now this thing is 0, and what we are left with is Na ln Na upon Na plus Nb, and Nb ln Nb plus Na. So now things are a bit familiar. Minus sign is there now also. This is nothing but Xa. So Na ln Xa plus Nb ln Xb. Now things are reduced. This R ln omega term is now reduced. So this configurational entropy was minus K, sorry, it was not minus, it was K ln omega, where ln omega is this thing, so K, now it is minus Na ln Xa plus Nb ln Xb. Let's multiply and divide by Na. So we'll get this Kna, we know that it is nothing but our gas constant. It will become minus R Na by capital Na, or you can say our Avogadro number, so Nb will become Xa ln Xa plus Xb ln Xb. Now we have got the final configurational entropy term as minus R Xa ln Xa plus Xb ln Xb. So we can write Now, for ideal mix, our G system will be XAGA plus XBGB plus delta G mix, which is delta H mix, minus T delta S mix, where this was 0, and this delta S mix is nothing but this, so we'll get XAGA plus XBGB plus RT XA ln XA plus XB ln XB. So this is our G system. We can combine XA again. We can get XA GA plus RT ln XA plus GB, or I should write here XB bracket GB plus RT ln XB. So in the next video we'll study what this term actually is, and we'll move on to the next type of mixture, which is regular mixture. I hope you understand the video. So I went through the proof pretty quickly. Just write that down once and you'll understand it. The main thing is we want to make this term ln 1, so we just divided by Na. For dividing Na, we have to just add and subtract this term. So that's all we did. So let's see. In the next video, we'll study about regular solution.